Late autumn of 1862 hit the northern Minnesota wilderness with a vengeance. When the first hard freeze locked the boreal forest, a second-generation homesteader watched ice form on his cabin floor 3 feet from his roaring hearth. He had built his shelter exactly like every other settler was told to build it. Central fireplace, raised floor joists, standard frontier design that burned through 2 cords of wood each week and still left his family shivering. Across the territory, homesteaders in identical cabins were losing the same battle against the cold, wasting precious timber and breathing smoke just to survive each night. But this trapper-turned-farmer quietly borrowed techniques from older traditions to create something his neighbors called a useless tunnel system. Local builders mocked his strange Y external firebox and called him wasteful. Yet when the brutal winter of 1863 hit with temperatures 30 below zero, his cabin stayed 50 degrees warmer than his neighbors while burning only half the wood. What did he understand about moving heat through stone and earth that every frontier builder had forgotten? The problem went deeper than just cold floors. By December, the standard cabin design revealed its full range of failures across the northern settlements. The trapper's neighbor to the east, a family of 5 crammed into a 16 by 20-foot cabin, kept their central hearth burning from dawn until midnight. Despite the constant fire, frost accumulated along the interior log walls where cold seeped through gaps in the chinking. Their youngest child developed a persistent cough from breathing smoke that lingered despite the chimney's supposed draw. The mother complained of headaches and burning eyes. Worse, condensation from their breath and cooking formed ice crystals on the inside walls each morning, creating a cycle of dampness that promoted mold growth where the logs met the raised wooden floor. The cabin to the west faced the same losing battle. The settler had followed every piece of frontier wisdom. He'd positioned his hearth dead center in the main room for even heat distribution, built his floor 3 feet off the ground to prevent moisture from seeping up through the soil, and constructed a proper stone chimney with adequate height for good draft. Yet his water barrels stored beneath the raised floor froze solid during the coldest nights, bursting the wooden staves and ruining weeks of stored drinking water. His root cellar vegetables buried in sawdust under the floorboards turned to mush when repeated freeze-thaw cycles destroyed their cell walls. The trapper observed these failures with the eye of someone who had spent winters in conditions that would kill the unprepared. His name was Jacob Petrov, son of a Balkan woodworker who had immigrated 15 years earlier with memories of mountain valley cottages that stayed warm through alpine winters. During his trapping seasons, Jacob had traded with Ojibwe and Dakota hunters who built winter camps designed around completely different heating principles. He had crouched in earth lodges where fires burned outside the living space, yet the interior stayed comfortable through the coldest nights. He had watched native builders heat rocks in external fires, then move the heated stones into covered pits beneath sleeping areas, creating warmth that lasted until morning. These experiences planted questions that conventional frontier wisdom couldn't answer. Why did everyone assume fire had to burn inside the living space? Why accept smoke and waste when other traditions had solved these problems generations ago? His father had described stone floors in Balkan cottages that stayed warm for hours after the fire died, heated by flues that ran beneath the floor stones before exiting through tall chimneys. The principle seemed clear: heat the mass, not just the air. When Jacob began sketching plans for a different approach, the resistance came swift and sharp. The local supply foreman, a weathered Irishman named Murphy, who had overseen cabin construction across 3 counties, examined Jacob's rough drawings with undisguised skepticism. The plans showed a firebox built into a small, external lean-to, connected to a stone-lined trench that would run beneath the cabin floor before connecting to a vertical flue on the opposite wall. "That's castle work," Murphy declared, jabbing a thick finger at the sketches. "You think you're building for some European lord? This is frontier country. We build fast, we build simple, and we don't waste time on fancy nonsense that'll just collapse come spring." Murphy had seen dozens of ambitious settlers arrive with elaborate plans, only to abandon them when the reality of frontier construction hit. "Mark my words, Petrov. Come February, you'll be begging for a proper hearth like everyone else." The neighboring homesteaders proved equally dismissive. They gathered around Jakob's cabin site during his initial excavation work, watching him dig a shallow trench beneath where his floor joists would sit. "Look at him mining for gold under his own house," one settler joked. Another shook his head in mock sympathy. "Poor bastard thinks he's building some kind of Roman bathhouse. Wait until he realizes he's just dug himself a nice basement full of frozen mud." The criticism stung because it contained a kernel of practical concern. Frontier life demanded efficiency above all else. Every hour spent on experimental construction was an hour not spent hunting, preserving food, or preparing for the next crisis. Resources were scarce, winter was unforgiving, and proven methods existed for good reason. Why risk family survival on untested ideas when conventional cabin design had kept settlers alive across the territories? But Jacob had seen the costs of conventional wisdom firsthand. His first winter in a standard cabin had nearly killed his wife during a week-long blizzard when their fire died during the night, and the interior temperature dropped to just 5 degrees above the outside air. He had burned through his entire winter wood supply by January, forcing dangerous trips into the forest during storms to cut more fuel. His children had suffered recurring respiratory infections from constant smoke exposure. His stored food had spoiled when repeated freezing damaged containers and spoiled preserved meat. The central conflict crystallized in his mind as he continued digging despite the mockery. Conventional frontier practice treated heat as something to be produced constantly and consumed immediately. Fire inside equaled warmth inside, end of discussion. But traditional knowledge from older cultures suggested a radically different approach. Heat could be stored in mass, controlled through proper airflow, and delivered efficiently without smoke or waste. The difference wasn't just technical, it represented two fundamentally different relationships with energy, resources, and survival. As autumn progressed toward the killing cold of a Minnesota winter, Jacob pressed forward with his underground construction. He lined his shallow trench with flat field stones, sealed the gaps with clay mixed with grass, and prepared to test whether ancient wisdom could outperform accepted frontier practice. The neighbors continued their jokes, but their laughter carried an undertone of nervous attention. If the crazy trapper's tunnel actually worked, it would expose the costly inadequacy of everything they thought they knew about staying warm. Jakob's construction began with understanding the fundamental physics that conventional cabins ignored entirely. Heat moved in 3 distinct ways: conduction through solid materials, convection through air currents, and radiation from warm surfaces to cooler ones. Standard raised floor cabins relied almost exclusively on convection, heating air that rose quickly to the ceiling and leaked out through gaps in the logs. This approach wasted enormous energy because air held heat poorly and moved constantly, creating drafts and uneven temperatures throughout the living space. Thermal mass offered a completely different strategy. Dense materials like stone absorbed heat energy slowly, but released it gradually over many hours, creating steady, comfortable warmth without constant fuel input. Jacob had observed this principle in his father's blacksmith shop, where the stone forge base stayed warm long after the fire died, and in native winter camps where heated rocks placed in covered pits provided overnight warmth. The challenge lay in adapting this knowledge to frontier construction, using only materials available from the immediate landscape. The stone selection process required careful attention to geological properties that most settlers never considered. Jacob walked creek beds and rocky outcrops, testing stones by striking them with a hammer to identify those that rang with a clear tone rather than a dull thud. Clear ringing stones indicated dense, non-porous material that would conduct heat efficiently and resist cracking under thermal stress. He rejected sandstones and shales that showed visible layering, focusing instead on granite field stones and dense limestone pieces that had survived countless freeze-thaw cycles without fracturing. For the trench foundation, Jacob excavated to a depth of exactly 18 inches below where his floor joists would sit, creating a channel 14 feet long and 3 feet wide that ran the full length of his cabin. The excavation revealed the critical importance of proper drainage. Minnesota's clay-heavy soil retained moisture that could freeze and heave, potentially destroying his stonework. He lined the bottom of the trench with 6 inches of coarse gravel scavenged from a nearby creek bed, creating a drainage layer that would prevent frost damage to his thermal mass system. The stone laying demanded techniques borrowed from European masonry traditions that few American settlers possessed. Jakob arranged his field stones in courses, with each layer overlapping the joints of the layer beneath to create structural integrity. The bottom course consisted of the largest stones, each weighing between 30 and 50 pounds, positioned to create a continuous heat-conducting surface. He selected stones with relatively flat tops and bottoms, rejecting rounded river rocks that would create gaps where hot gases could escape without transferring their energy to the thermal mass. The mortar composition proved crucial to the system's effectiveness. Jakob mixed local clay with coarse sand in a 3-to-1 ratio, adding chopped grass and animal hair to prevent cracking as the mixture dried. This combination created a seal that was both heat-conductive and flexible enough to expand and contract with temperature changes without breaking apart. He learned through trial and error that mortar joints thicker than 1 inch wasted heat energy, while joints thinner than half an inch cracked under thermal stress. The stone courses rose in precisely measured layers. The second course added another 6 inches of height, bringing the total thermal mass to 12 inches thick. Jakob positioned these stones to create small channels between them, ensuring hot exhaust gases would contact maximum stone surface area as they traveled from the firebox to the exit flue. The top course received the most careful attention, as these stones would directly contact his cabin floor and needed perfectly flat surfaces to support the wooden planks above. Construction of the external firebox required adapting Balkan techniques to frontier materials. Jakob built a small lean-to structure against his cabin's south wall, positioning the firebox opening to face away from prevailing northwest winds that could interfere with proper draft. The firebox itself measured 2 feet square and 18 inches deep, sized to accommodate split logs while maintaining efficient combustion. He lined the interior with fire-resistant stones and connected the rear wall directly to his underground thermal mass channel. The exhaust system demanded precise engineering to ensure proper gas flow without backdraft or stagnation. Hot combustion gases needed to travel the full 14-foot length of his stone channel, transferring their heat energy to the thermal mass before exiting through a vertical flue on the cabin's north wall. Jakob calculated that the flue needed to extend at least 8 feet above the exit point to create sufficient draft for consistent gas flow, even during calm weather conditions. The first test firing revealed both the promise and the challenges of his thermal mass system. Jakob loaded the firebox with split oak and birch, lighting a fire that burned intensely for approximately 2 hours. The exhaust gases traveled through his stone channel, heating the thermal mass to temperatures uncomfortable to touch with bare hands. However, initial heat distribution proved uneven, with stones near the firebox reaching much higher temperatures than those near the exit flue. This led to his most important technical refinement, the creation of heat distribution channels within the thermal mass itself. Jakob carefully removed selected stones from his top course and chiseled shallow grooves into their undersides, creating branching pathways that forced hot gases to contact more stone surface area before exiting. This modification distributed heat more evenly throughout the entire thermal mass, eliminating hot spots and cool zones that had characterized his initial attempts. When Jakob finally laid his cabin floor over the completed thermal mass system, the transformation became immediately apparent. Walking across the wooden planks, he could feel consistent warmth rising through the boards. The stone mass beneath continued radiating heat for more than 12 hours after his fire died, maintaining comfortable floor temperatures that eliminated the bone-chilling cold that plagued conventional raised floor cabins throughout the long Minnesota winter nights. The completion of Jakob's thermal mass system revealed a new set of technical challenges that conventional fireplace design had never adequately solved. Standard indoor hearths created negative air pressure inside cabins, forcing cold outside air to infiltrate through every gap and crack in the log walls. This infiltration not only wasted heat energy, but also created unpredictable downdrafts that could blow smoke back into living spaces during certain weather conditions. Jakob needed to engineer a combustion system that would maintain proper draft while preventing his cabin's interior air from being sucked into the combustion process. The solution required understanding barometric pressure dynamics
that few frontier builders had ever considered. Hot gases naturally rise, but only when the pressure differential between the
combustion chamber and the exit point creates sufficient draw. Jakob calculated that his vertical flue needed to extend precisely 8 feet above his cabin's roofline to generate adequate natural draft, but he also had to account for wind patterns that could disrupt airflow. Prevailing northwest winds could create downdrafts that would force exhaust gases back through his thermal mass channels, potentially filling his cabin with deadly carbon monoxide. Jakob addressed this challenge by designing a wind-resistant flue cap using principles he had observed in Native American fire management techniques. He crafted a simple cover from hammered metal scraps, positioning it 6 inches above his flue opening and angled to deflect wind while maintaining vertical draw. The cap design included 4 small openings on the downwind side, allowing exhaust gases to exit regardless of wind direction while preventing rain and snow from entering the system and extinguishing his fires. The combustion air supply system demanded even more sophisticated engineering. Standard fireplaces drew air from inside the cabin, creating the negative pressure that plagued conventional designs. Jakob needed to provide his external firebox with adequate oxygen for complete combustion without stealing heated air from his living space. He solved this by constructing a dedicated air intake channel that ran underground from a point 30 feet upwind of his cabin to a position directly beneath his external firebox. This air supply tunnel measured 6 inches in diameter and descended 18 inches below ground level to prevent freezing during extreme cold snaps. Jakob lined the tunnel with clay tiles salvaged from a failed pottery operation in the nearest settlement, creating a smooth pathway that minimized airflow resistance. The tunnel terminated in a simple but crucial feature: an adjustable damper made from a flat piece of metal that could regulate the volume of combustion air entering his firebox. The damper system allowed Jakob to control his fire's intensity with precision impossible in conventional hearths. By partially closing the air intake, he could slow combustion and extend burn times, making each load of split wood last significantly longer. Conversely, opening the damper fully provided the intense heat needed to quickly warm his thermal mass during the coldest weather. This level of control transformed fire management from a constant struggle into a predictable, efficient process. The interaction between his air supply system and thermal mass channels created unexpected benefits that revealed the sophisticated physics underlying his design. Cool combustion air entered his firebox from below, while hot exhaust gases exited through his underground thermal mass channels before rising through his vertical flue. This created a continuous circulation pattern that maintained steady draft even during windless conditions that would cause conventional chimneys to struggle. Jakob's first extended test of the complete system occurred during a December cold snap that pushed nighttime temperatures to 15 degrees below zero. He loaded his external firebox with a carefully measured load of split oak, approximately equivalent to 30 pounds of seasoned wood. The fire burned intensely for exactly 90 minutes, heating his thermal mass to temperatures that made the cabin floor uncomfortably warm to walk on barefoot. Most remarkably, the air quality inside his cabin remained completely unchanged throughout the burning process. No smoke odor penetrated the living space, and the air remained fresh enough that his family could sleep comfortably without the burning eyes and scratchy throats that plagued occupants of conventional cabins. His wife noted that their water bucket, positioned near the cabin's north wall, showed no signs of the soot accumulation that typically coated everything in standard heated cabins. The fuel efficiency gains exceeded Jakob's most optimistic projections. His 90-minute fire provided comfortable warmth for approximately 16 hours, with the thermal mass continuing to radiate heat until the following evening. In contrast, his neighbors' indoor hearths required constant feeding throughout the day and night, consuming roughly 4 times as much split wood to maintain comparable interior temperatures. The exhaust gas temperature measurements provided crucial data for optimizing his system's performance. Jakob used a simple but effective method for monitoring gas temperatures, inserting iron rods into his flue at measured intervals and observing how quickly they heated. Gases entering his thermal mass channels measured uncomfortably hot to touch within minutes of lighting his fire, while gases exiting into his vertical flue had cooled to temperatures that barely warmed the iron rods.
This temperature differential proved that his thermal mass system was successfully capturing and storing the heat energy from his combustion gases rather than allowing it to escape unused into the atmosphere. The cooler exhaust temperatures also reduced the risk of chimney fires, a constant danger in conventional systems where superheated creosote deposits could ignite and destroy entire cabins. As winter deepened and Jakob's system proved its reliability, neighboring settlers began paying closer attention to the technical details of his unconventional heating approach. They observed that his external firebox produced no visible smoke after the first few minutes of each firing, indicating complete combustion that wasted no fuel energy. They noticed that his cabin showed no signs of the interior condensation that plagued their own homes, suggesting superior humidity control through proper ventilation management. The growing interest from his neighbors marked the beginning of a gradual shift in local building practices, as practical results began to overcome initial skepticism about Jakob's innovative
combustion and ventilation systems. Even with his revolutionary thermal mass and combustion systems operating flawlessly, Jakob discovered that his cabin's building envelope leaked precious heat energy through pathways that conventional frontier construction completely ignored. Every gap between logs, every crack around door frames, and every unsealed joint in his roof system created air infiltration routes that could nullify the efficiency gains of his heating innovation. The physics of heat loss through building envelopes involved complex interactions between air movement, conductive materials, and radiant heat transfer that demanded systematic solutions beyond what most settlers ever attempted. Jakob's diagnostic approach drew from his father's European carpentry experience, where winter survival depended on understanding exactly how buildings lost heat. On a calm January morning with exterior temperatures at 10 degrees below zero, he used a simple but effective technique to identify air leaks throughout his cabin structure. Lighting a candle, he moved methodically along every wall seam, door frame, and roof junction, watching for flame movement that indicated air infiltration. The results revealed dozens of heat loss pathways that would have remained invisible without this systematic inspection. The log wall gaps presented the most significant challenge. Standard frontier chinking used whatever materials were immediately available, typically mud or clay mixed with grass or moss. This approach created temporary seals that cracked and fell out during freeze-thaw cycles, leaving gaps that allowed cold air infiltration and warm air escape. Jakob needed a chinking compound that would remain flexible through temperature extremes while providing superior thermal insulation properties. His solution combined techniques from Balkan mountain construction with materials available in the Minnesota wilderness. Jacob harvested clay from a creek bank 2 miles from his homestead, selecting deposits with high plasticity that would resist cracking. He mixed this clay with coarse sand in a 2-to-1 ratio to provide structural strength, then added chopped animal hair from deer hides and dried grass in quantities equal to roughly 1/4 the volume of his clay sand mixture. The critical innovation lay in his addition of pine pitch as a binding agent and waterproofing component. Jakob collected resin that oozed from damaged pine trees, heating it carefully over coals until it reached a honey-like consistency. He incorporated this warm pitch into his clay mixture while it remained workable, creating a chinking compound that would cure into a flexible, waterproof seal. The pine pitch also provided natural antimicrobial properties that prevented the mold growth common in conventional mud chinking. Application of this advanced chinking required techniques that went far beyond simply stuffing gaps with mud. Jakob first cleaned each log seam with a thin knife blade, removing all old chinking material and debris that could prevent proper adhesion. He then carved shallow grooves into the log surfaces on both sides of each gap, creating mechanical anchors that would hold his new chinking compound securely in place, even during the wood expansion and contraction cycles that plagued frontier construction. The floor insulation system addressed heat loss pathways that conventional raised floor cabins never attempted to control. Despite his thermal mass providing radiant heat from below, significant energy still escaped downward into the cold soil beneath his cabin. Jakob created an insulating barrier by spreading a 4-inch layer of dried leaves, sawdust, and animal hair between his heated stone mass and the soil below. This natural insulation prevented conductive heat loss while allowing his thermal mass to focus its energy on warming his cabin interior. Above his stone thermal mass, Jakob installed an additional heat-retaining layer that transformed his floor into a sophisticated thermal control system. He mixed clay with fine sand and spread this mixture in a 1-inch layer directly over his heated stones, creating a smooth, heat-conductive surface that would distribute radiant energy evenly across his cabin floor. Over this clay layer, he placed thick deer hides treated with pine pitch to create a waterproof insulating floor covering that retained heat while remaining comfortable for daily activities. The door and window sealing systems required engineering solutions that addressed both air infiltration and the practical needs of frontier life. Jacob constructed what European builders called a thermal vestibule, essentially creating an airlock entry system that prevented cold air from rushing directly into his heated cabin each time the door opened. He built a small enclosed porch extending 4 feet from his main door, with its own exterior door positioned to create a buffer zone between outside temperatures and his cabin interior. Inside this vestibule, Jakob installed an innovative door sealing system that eliminated the gaps around door frames where conventional cabins lost enormous amounts of heat. He carved rabbit grooves into his door frame, creating recessed channels that accepted flexible sealing strips made from deer hide stuffed with animal hair. When his door closed, these strips compressed against the door edges, creating a nearly airtight seal that prevented air infiltration while remaining easy to operate during daily use. Window thermal control presented unique challenges since glass was unavailable and animal hide coverings provided minimal insulation value. Jakob developed a seasonal window sealing system using hinged wooden shutters lined with layers of treated hide and packed with deer hair insulation. During the coldest months, these shutters remained closed, eliminating heat loss through window openings, while maintaining a small central panel that could open briefly for light and ventilation during warmer parts of the day. The roof sealing system addressed convective heat loss through the cabin's highest point, where warm air naturally accumulated and escaped through gaps in conventional log construction. Jakob packed moss and clay mixture into every joint between his roof logs, then covered the exterior with overlapping bark sheets sealed with pine pitch. This created a continuous thermal barrier that prevented heat loss while shedding rain and snow effectively. His most sophisticated envelope control involved seasonal adjustments to his thermal mass system output. Jakob discovered that his spring and fall heating needs differed significantly from deep winter requirements, demanding variable heat output that his fixed thermal mass system couldn't provide. He solved this by installing adjustable dampers in his thermal mass channels, allowing him to redirect exhaust gases around portions of his stone mass during milder weather, reducing heat output while maintaining complete combustion and proper draft. The completed building envelope system demonstrated remarkable thermal performance improvements over conventional frontier construction. Jakob's systematic sealing eliminated virtually all air infiltration, while his insulation layers prevented conductive heat loss through floors, walls, and roof. Combined with his thermal mass and combustion innovations, the sealed envelope created a cabin that maintained stable interior temperatures with minimal fuel consumption throughout the harshest Minnesota winter conditions. The ultimate test of Jakob's integrated heating system arrived without warning in late January of 1863, when an Arctic air mass descended from the Canadian wilderness and locked the northern Minnesota territory in a grip of unprecedented cold. Weather records from military outposts would later document this as the most severe cold snap in territorial history, with nighttime temperatures plunging to 30 degrees below zero and remaining there for 14 consecutive days. Daytime highs never rose above 10 degrees below zero, while howling northwest winds created wind chill conditions that could freeze exposed skin within minutes. The extreme cold revealed performance characteristics of heating systems that normal winter conditions never tested. Jakob's neighbors, burning fires continuously in their conventional cabins, faced a crisis of fuel depletion that threatened their survival. The Anderson family to the east consumed their entire remaining wood supply by the end of the first week, forcing the father to venture into the deadly cold to cut green timber that burned poorly and produced minimal heat. Their cabin interior temperature dropped to within 5 degrees of outside air during the coldest nights, creating life-threatening conditions for their youngest children. The Murphy cabin experienced catastrophic system failures that demonstrated the vulnerability of Conventional designs under extreme stress. Their central chimney, subjected to repeated heating and cooling cycles, developed cracks that allowed cold air infiltration directly into their living space. Ice formed on their interior walls despite maintaining fires around the clock, and their wooden water containers split when the contents froze solid. Most dangerous of all, their desperate attempts to generate more heat by overloading their hearth created chimney fires that threatened to burn down their entire structure. Jakob's systematic approach to documenting his system's performance during this extreme weather event provided precise data that would later influence heating design across the region. He maintained detailed logs of fuel consumption, interior temperatures, and firing schedules that demonstrated the remarkable efficiency of his thermal mass system under the harshest possible conditions. Each evening, he recorded exterior temperatures using a simple but accurate method, observing the freezing characteristics of different solutions placed outside his cabin, from water that froze at 32 degrees to alcohol mixtures that remained liquid at much lower temperatures. His fuel consumption records revealed performance gains that exceeded even his optimistic projections. During the 14-day cold snap, Jacob burned a total of 1½ cords of seasoned oak and birch, maintaining comfortable interior conditions throughout the entire period. His firing schedule remained remarkably consistent. One 90-minute burn every 24 hours, typically started in early evening to provide maximum overnight warmth. This contrasted dramatically with his neighbor's consumption of 3 to 4 cords per week, burning fires continuously day and night with inferior results. The thermal mass system's heat retention capabilities proved most impressive during the coldest nights when exterior temperatures reached their lowest points. Jakob's detailed temperature measurements, taken using iron rods placed at various locations throughout his cabin, showed interior temperatures that remained 25 to 30 degrees warmer than outside conditions. Most remarkably, his cabin floor stayed warm enough to walk on barefoot even 12 hours after his evening fire had completely burned out, demonstrating the superior heat storage capacity of his stone mass system. Documentation techniques that Jacob developed during this extreme test period would later become standard practices for evaluating heating system performance. He created a simple but effective method for measuring heat distribution throughout his cabin by placing containers of water at different locations and recording their freezing characteristics. Water near his thermal mass channels remained liquid throughout the cold snap, while containers placed near exterior walls showed only thin ice formation during the coldest nights, indicating remarkably even heat distribution. Compared to conventional cabins where water froze solid everywhere except directly in front of active fires. The social transformation began subtly as neighbors observed Jakob's cabin, showing no signs of the distress that plagued every other structure in the settlement. Smoke never poured from his chimney except during his brief evening fires, yet his windows never showed the frost accumulation that coated the glass of conventional heated cabins. Children playing outside noticed that snow melted completely around Jakob's cabin foundation while remaining frozen against other buildings, providing visible evidence of superior heat retention and minimal heat loss. The first documented adoption of Jakob's techniques occurred when his neighbor Thomas Kellerman, facing potential death from fuel depletion, asked to observe Jakob's firing procedure and examine his external firebox design. Kellerman spent 2 days studying the thermal mass construction and took careful measurements of the stone channel dimensions, air intake system, and flue arrangements. Within a month, Kellerman began modifying his own cabin by adding external combustion capability and installing primitive thermal mass elements beneath his floor. Local supply merchants provided inadvertent documentation of the system's growing influence through their inventory records. Demand for flat field stones increased dramatically during the spring of 1863, as did orders for clay materials suitable for chinking and sealing applications. The Territorial Supply Company noted unusual requests for metal components needed to construct external fireboxes and flue systems, indicating that multiple settlers were attempting to replicate elements of Jakob's design. Word of Jakob's heating innovation spread through established communication networks that connected frontier settlements across the Northern Territories. Trading post operators, traveling merchants, and seasonal hunters carried descriptions of the thermal mass cabin to communities hundreds of miles away.
Military personnel stationed at frontier outposts included references to underground heating systems in their official reports, noting potential applications for improving soldier comfort and reducing fuel requirements at remote installations. The long-term architectural influence became evident within a decade as builders across cold climate regions incorporated elements of Jacob's integrated approach into new construction projects. The combination of external combustion, thermal mass heat storage, and systematic envelope sealing evolved into recognized building techniques that appeared in homesteading guides and territorial construction manuals. These publications credited traditional knowledge sources while adapting the methods to local materials and conditions available in different geographic regions. By the 1870s, variations of Jacob's thermal mass heating system had spread throughout the northern Great
Plains and mountain territories adapted to local stone types, climate conditions, and available materials. The core principles remained consistent: separate combustion from living space, store heat and thermal mass, control air infiltration, and maximize fuel efficiency through complete combustion and heat recovery. These innovations demonstrated that frontier survival could be improved dramatically by combining traditional knowledge from multiple cultures with systematic engineering approaches that prioritized long-term sustainability over quick construction methods. The quiet revolution in heating technology that began with one settler's refusal to accept conventional wisdom ultimately transformed how entire regions approached the challenge of surviving harsh winter conditions while conserving precious fuel resources.